In this first video on logarithms, there's going to be a lot of things that we're going to go over. So if you need to, make sure you pause and rewind if you need to review something or if I go too fast. But first of all, the definition of a logarithm. And it comes from an exponential equation. And the definition says that if y equals b to the x, then the log base b of y equals x. So take a look at how do we go from here to here. Notice that the base of the exponent and the base of the log are the same, but for the exponent it was b to the x. For the log, it's log base b of y. So they keep the same base but switch the other two around. So let's just practice switching between exponential and logarithmic forms. So this first one, 4 squared equals 16, that's a true statement, but how do we write it in terms of logarithms? Well, what we do is we keep the same base, 4, and we switch the other two around, the 2 and the 16. So it's going to be log base 2 of 16, or log base 4 of 16 is equal to 2. Let's do it again when it's all variables. Keep the same base, w, and switch the other two around. So it's log base w of r is equal to n. How about if we're given logs? Let's turn them into exponential equations. So we keep the same base, 2, and switch the other two around. So 2 to the third power equals 8. When it's all letters, it doesn't matter. Keep the same base, b, and switch the other two around. So b to the x equals n. This can be helpful when we need to evaluate a log, like log base 4 of 64. What we should do is just set it equal to x. Alright, so then whatever we find out x to be, that's going to be what the log base 4 of 64 is. Now turn it into an exponential equation. 4 to the x power equals 64. And how we could solve this is just by using our number skills and guessing and testing. Well, let's check 2. Is 4 to the second equal to 64? Nope. 4 to the second is 16. How about 4 to the third? Is that 64? Yep, sure is. That means that x is equal to that power, 3. Right. So let's try it again here. Again, log base 36 of 6. Let's just set it equal to x. Turn it into an exponential function. 36 to the x is equal to 6. Well, I know square root of 36 is 6. So that would mean that 36 to the 1/2 is equal to 6. Because that'll give us the square root of 36. Okay. So our solution, x, is equal to the power 1/2. Now you might have grabbed your calculator and tried to punch these in and run into a couple of problems. Well, the main problem is there isn't a log base 4 button or a log base 36 button. There are two special types of logarithms. They're called the common log and the natural log. The common log is log base 10. So if we have log base 10 of any number, we write that as the common log by not writing the base. So we just say log of x. This button is on your calculator. So if you needed to find the log base 10 of 8, you could just type that into your calculator, and that would give you the value of 0.903. There is another special log on the calculator. It's called the natural log. And what the natural log is log base e, that natural number. And how it's abbreviated is ln. So you might notice the ln button probably right next to the e button on your calculator. So that if you needed to find the natural log of, say, 0.3, you can type that into your calculator, and you should do that right now, and make sure that you get negative 1.203. Next, I want to run through a couple of seemingly tricky problems that turn out to be super easy. First of all, let's say we want to find out what log base b of b to the x is. We got a lot of stuff in there, but what you should do is just set it equal to, and I'm just picking another variable, so that we're going to simplify this expression. Now, convert it from a logarithmic expression or equation into an exponential equation. So we would keep the same base, this base, and switch the other two around. So we would switch these two around. So let's do that. We're going to keep the same base, the yellow b, and then switch the other two. So b to the n is equal to b to the x. And now it should be fairly obvious that n is equal to x. And that is huge because we said that n is our solution, x. Therefore, if we have log base b of b to the x, it's going to equal x. It might seem like a completely random statement, but let's take a look at it. I mean, something really awesome is happening right here. When we have the base of the log and the base of the exponent are equal, these things end up canceling each other, and all we're left with is x. That's super nice. I wonder if it works the other way around, if you have b to the log base b of x. Let's do that same process where we set it equal to n first, and then turn it into a logarithmic expression. We're going to keep the same base and switch the other two around. So we're going to switch these two around. So I'm going to have a log with that yellow base, b, and then switch the two greens around. Of n is equal to log base b of x. And it should be fairly obvious once again now that these two are equal to each other. N equals x. Giving us that super sweet result again, that b to the log base b of x is equal to x. That means, once again, that, oops, hold on. Right here. Once again, we have that if the base of the exponent and the base of the log are the same, they cancel each other out. So it takes a fairly complicated looking expression and turns it into a simple one pretty quickly. So if we need to evaluate these two expressions, at first they might look intimidating, but we notice that the base of the exponent and the base of the log are the same. So this thing is just going to simplify to 37. In the next one, base of the log and the base of the exponent are the same. So this thing is going to simplify to -9. Super sweet. Lastly, let's take a look at some graphing. The parent function, y equals log base 2 of x. And if we're going to graph this, I want to look at it in terms of an exponential function. So we'll keep the same base and switch the two around. Because how do we graph when we don't know how to graph? Well, we set up a table. And we're going to need to pick some points. Normally we pick x's, but since I'm going to look at this expression as 2 to the y equals x, I'm actually going to pick y values. I'm going to pick 0 because I can find out that 2 to the 0 is just 1. And then I'll pick 1 because 2 to the first is 2, and -1 because 2 to the negative first is a half. I'll do 2 because 2 squared is 4, and I'll do -2 because 2 to the -2 is 1/4. And that gives me a lot of points to plot. But let's start plotting them and see what happens. 1, 0, 2, 1, 1/2, -1, 4, 2, and 1/4, -2. And we end up with a curve that looks familiar. It kind of looks like an exponential curve. Alright, except an exponential curve started small and got big, but in the y direction like this. Started small and then it got big. That was an exponential curve. This is a logarithmic curve. So what are the domain and range for this? If you look, when we're talking about domain being the x values again, we don't get to keep all of the x values. And we don't get to use all the x values. There's this vertical asymptote right here at x equals 0. And the entire graph stays to the right of that. So that means that the domain for a log function is going to be all x's that are greater than 0. The range, however, goes all the way down to -infinity, all the way up to +infinity. So the range this time is going to be all real numbers. And when we thought about our exponential graph, these two were kind of switched around, where the domain was all real numbers and the range was the y-coordinates being greater than 0. So we have something happening here between these two. Their graphs look very similar, but their domains and ranges are switched around.